Okay, welcome to day 3 or night 3, I guess, maybe, whichever, evening 3. Um, so I see that we are missing a couple people, but I'm recording it, so hopefully it won't be a problem. I've been sending out the links to all the previous recordings. Have you guys gone in and looked at those? You found those to be helpful at all?
I watched the second class again today to try to pick up some pieces.
Yeah, I think it's very convenient. Having these recordings is actually very good. Um, in fact, I think because of the recording capability, that makes it actually better to have classes online here than if we'd had them in person, because you don't get the recordings that way. So let me share my screen and let's go ahead and jump in. All right, so here is the agenda for today. Let me change this. Okay. All right. So let's see, hang on a second. I want to make sure that, okay. All right, so here's the agenda. We're going to do a little bit of review, and then we're going to start into new material. We're going to talk about celestial coordinates. You may have heard terms of GHA, SHA, declination, stuff like that. So tonight you're going to find out what those mean and how we use them. And now last time we started the process of reducing a star site without your smartphone. Today we're going to finish the process, but we are going to keep the numbers simple. So when we put in the numbers, in the cases where it's possible, we're going to put them in as integer degrees. So our latitude, instead of being 16 degrees and 37.5 minutes, we're just going to call it 16 degrees. And all and similar type things. In order to keep the numbers simple, because then, in my opinion, the number one reason why people think celestial navigation is hard is not because the celestial navigation portion of it is hard. It's all of the little details, like how do you handle the fact when your latitude is not exactly 16 degrees? How do you interpolate between 16 and 17? So interpolation is a word that you're going to become very familiar with. But today I'm going to try to avoid the interpolation. We're going to stick with simple numbers because I want you to focus on the process. I want you to see the process and realize that the process is not as bad as you may have heard. And then toward the end of the day today, if we have time, and definitely on next week's class, then we'll start dealing with what do you do when it's not an integer? How do you interpolate and all those types of things. And then the last thing that we will definitely do today for sure is we'll learn how to plot your position on what's called an open ocean chart and why you need that. I'll talk more about that when we get to it. So anyway, that is the plan. So let's do a little bit of review first. Okay, so yeah, here's the agenda for day 4. Um, so how to reduce the site when the numbers are messy. Also, a noon sunshot. Now, this is really important because back in the day, before the GPSs existed, and people had to do celestial navigation because that was the only choice, most people did not do star shots. Most people would do what's called a noon sunshot, where they would go out a little bit before noon, they'd take some measurements, and then every couple minutes they'd take measurements until the sun reaches the highest point and then the sun starts going back down again. And so then they take those numbers and crunch those, and from that you can figure out your latitude and longitude. And the math is way simpler. And so that's what most people did. So doing evening or morning star shots requires a little bit more math, but not that much. And also the moon. The moon is a special case. There's a couple of peculiarities with there. And then the last thing that we will do on the last day of class is we'll talk about how to do Polaris shots. And when I say Polaris, I mean the North Star. And a lot of people say, well, what is there to do? I mean, you measure the altitude of the North Star and bingo, that is your latitude. Well, yeah, maybe not, because the North Star, although it's very, very closely aligned with the Earth's axis, it's not exactly on the Earth's axis. Now, so if you're willing to tolerate some error, then yeah, you can just measure the altitude and call it good. But if you want to get high accuracy, you need to account for the fact that Polaris is not exactly on the Earth's axis. So we'll talk about that last day. Okay, so first thing that I want to know is, were either of you able to go to the shore of Utah Lake or Great Salt Lake and use your sextant and get any star measurements?
I was on spring break last week and didn't take it with me. And when I got here, it has been cloudy. And I haven't gotten a break in the clouds to do anything yet with.
Okay.
I'm hoping, because it's supposed to be sunny the rest of the week, to be able to, well, a lot of the rest of the week, to be able to do that.
Okay. Now, when you say spring break, that reminds me of a question I should have asked on day one. Does that mean you're a teacher?
My wife is,
Oh,
and
okay.
she wanted to go see her mom. And so I took some time off.
Okay. What do you do for a living?
I am a prosecutor in juvenile court.
Ah, okay. How about you, Alex? Did you have any luck getting any sextant measurements?
I did. So I
Oh.
went on Friday evening to Linden Marina in Utah Lake,
Mhm.
and I took 4 star measurements. And it's interesting how I could kind of tell which ones, like I had kind of a gut feeling about ones that weren't quite right. So there was one that was way off, and then but the other 3 were great. It put me about 20 miles away in the Wasatch Mountains. So
Wow.
as the crow flies, yeah, not bad at all. I was
And
very, very excited.
especially considering the fact that you were using a Davis Mark III. If you
Oh yeah,
if you can get within 20 miles using a Davis Mark III, that is good. That is really good.
I was surprised. I was very surprised at how well it went. So really exciting.
Okay. All right. Well, I'm glad to hear that. And so hopefully you'll get more chances that we can do that. And you know, what I am thinking is that if you guys would like to, I would be willing to have a, maybe call it a star party, where we could go together to the shore of Utah Lake or wherever, either some evening. I'm not a morning person, so let's talk in the evening. Or the other possibility is that we could do a noon sunshot. So what we could do is sometime shortly before noon, we could go to the lake, and then we could take some measurements. Like I said earlier, the way noon shots do is a little bit before noon, you start taking measurements, and then you keep taking those measurements until a little bit after noon has passed. So that way we could do it in the middle of the day. So is that something that you guys would be interested in doing?
Uh-huh.
Okay. All right.
Yes,
Okay. All right.
I
So,
would love to
we'll
do
do
something
that.
like that.
Okay. So between now and next time, I'll look at my availability and you guys look at your availabilities. We could, would you be more interested in doing an evening session where we measure some stars, or does the noontime session sound more appealing to you?
Either one.
Either one. I mean, I would have to do the noontime one. Would have to be a weekend.
Yeah. For me,
obviously.
for sure. Yeah.
Okay.
Does that
But-
have to be at 11 because of daylight savings time?
It has to be at 1 actually, because
At
I go at
1.
the same time. Go the other way.
Oh, jeepers.
Yeah. So local noon for us here in Utah is going to occur sometime around 1 o'clock. But next time we meet, I'll show you how to calculate. If you know what your longitude is, you can calculate ahead of time what time local noon is going to occur. So we'll talk about that next time. So that might be a good way to do it. And maybe I could even arrange to get a boat. Now I'm not guaranteeing anything, but I might be able to arrange to get a boat and we can go down out on the water and take measurements on the water. That'd be really good.
That would be so cool.
Okay. I'll
Is there gonna
look
be
into that.
Is there going to be enough water in the lake this summer for people to sail? Because there's no snowpack.
That is a concern. That is definitely a concern. Yeah.
It'll be
Okay.
enough for at least a couple months.
Yeah, maybe through June, July, but after that, pretty iffy. Okay, so all right, got that. One thing that I do need to tell you is that last time when I talked about how to adjust the mirror to get rid of any index error that you might have, I kind of oversimplified things a little bit. And now I don't want to take the time to go into all the gruesome detail, but you do in fact have two screws, not just one. And if you really want to do it right, you want to use both screws. So let me recommend that if you read chapter 9 in your textbook, I think the author does a really good job of explaining how to adjust your mirror to get your sextant dialed in just perfectly. So let me just recommend that you read chapter 9, and I think you'll be happy with that. I like the job he does there. Okay, when you well, were you able to work on problem number 67? And now the one on the left, object number 1, we did that one together by ourselves. And we kind of sort of started in object 2, but we didn't finish it. Were you guys able to spend any time working on problem number 67 by yourself?
Yes.
I did.
Okay, and were you able to get the same numbers that I got here?
Yeah, looks like it.
Okay, all right, that's encouraging.
Oh, I was slightly off because of parallax correction. Where, oh, that's, where do you find that in the charts?
Okay,
Because I made that, I had that same issue with problem 68 as well, but that was the
Yeah.
one thing I couldn't figure out how to find.
yeah. Well, for the planets, it's pretty easy. For the moon, it's a little complicated. But for the planets, if you go to page 246 in your textbook, then you'll have a page from the nautical almanac. So remember, the real thing that you want is a nautical almanac. But if you look on page 246, we have some sample pages taken from the nautical almanac. If you look in the very center, you'll see it says stars and planets, right? And then there's this column here where it says additional correction. And then it's got Venus, and it's got a couple different months. And then you go down a little further and it's got Mars, and there's a couple different months. So this additional correction, that's the parallax correction.
Oh.
Okay, so for us, for us, it was May, right? So we go down here, we find Mars, and we look and we see that if it's any time between January 1st and July 5th, the parallax correction is, if you're anywhere between 0 and 60 degrees, you add 0.1. Now, if it's later in the year, then it's a slightly different number, because sometimes Mars is closer and sometimes Mars is farther. So it makes sense that the parallax correction would vary according to the month. But that's where you get it from, right there.
Thank you.
Now, the moon is a special case. The moon is so close that it's got some serious parallax error. And so I'm not even going to attempt to talk about the moon today. I've got time reserved next week where we'll talk about how to do the moon. It's got its own page. When you get a nautical almanac, you'll find that the moon has its own little section with its own little pages, because it's a little bit tricky.
So that was on page 68, which I thought we were supposed to do, and I got stuck there.
You mean problem 68?
Yeah.
Okay. Yeah. And this is a major oops on my part. I should have told you to hold off on the moon, and I did not. So my bad. I sincerely apologize.
No problem.
Yeah, but hopefully you were able to get object number 1. Were you able to do that? Okay, good.
Yeah, I just got, when it got to the refraction limb correction on the moon, I was just going, what?
Yeah, that's my bad. I should have warned you not to even attempt that. But we will talk about it next time, so you'll learn how to do it then. Okay, now I didn't officially assign any review problems, but there, some of the problems were intended to help review some of the concepts that we went over. And then every year, well, many years, I have some students who like to look ahead. And so they start doing some of these problems that having to do with GHA and SHA, even though we haven't yet talked about them. Are there any of these that you want to discuss, or you want to just go ahead and jump into today's material?
Can you go to 46? Problem
46.
46.
Okay. Hard to read on the screen there. Let me look it up on the book here. What page is it on?
34, 24, sorry.
24. Okay. And let me get my glasses. Can't read anything without those. Okay, got it. So do you have a specific question?
Yeah, how do you figure that out?
Okay.
I was having some kind of trouble with that.
All right. So you take this form, take these same forms that we see right here. And so hang on a sec while I get this. Okay. So just pretend that these numbers are there, just erase them out.
Right.
And so what we're going to do is we're going to take the sextant reading. Okay, so we put in the sextant reading right here. And I shouldn't have called it apparent altitude. That's probably not, I should have used a better, I should have called that the sextant altitude because that was my intention. Okay, so let's say that the sextant altitude is 16 and we measure it from eye height of 5 feet. So what we need to do then is we need to look up and see what is the, well, index correction, did I say? Okay, all right, so here we go. So the sextant reads negative 0.3 when it's supposed to read 0. Okay, so when we measure something on the sextant, if it's here, let me write this in here. So if the sextant reading is 16 degrees and 42.6 minutes. Okay, all right, so the index correction, are we going to add 0.3 or are we going to subtract 0.3? Okay, so if it's supposed to read 0 and it reads negative 0.3, that means that the numbers are all going to be too low, a factor of 0.3. So that means that our index correction should be a positive 0.3. Does that make sense? Okay. And then for our eye height, what we'd need to do is we'd need to look in the table to find out what is the dip correction for 5 feet. So we go to page 246 of our book, and we go over to the very most right column. And the numbers that sailors are usually concerned about are right here. All these other numbers, those are for big ships. Those numbers are way higher than a recreational sailor is going to do. Right here is where we can get the numbers for 5 feet. And you'll see that they don't have a correction for 5 feet, but they do have one for 4 feet and they do have one for 6 feet. Right? So the one for 5 feet then would be halfway in between.
Yeah.
So what's the number that's halfway in between negative 1.9 and negative 2.4?
Well, there's not an integer.
So it's not an integer, right?
You just round up or what?
You could go either way. There isn't a good argument for either rounding up or rounding down.
Okay.
So let's say let's round up. Okay. So I'm thinking 2.2. Okay.
Okay.
And notice it's got a minus sign in front of it. Okay. So that means that we would need to subtract 2.2, and these are always minutes. These are never going to be degrees. All right. So then what we do is we take 16.42, we add 0.3, we subtract 2.2, and whatever we get, that is our partially corrected height.
Okay.
Now, we aren't finished yet because we need to worry about the refraction correction. So what we do then is we go back here to page 246 again. And the middle columns there, the ones for the stars and the planets. So we want, we've got the numbers here, not the additional correction, but just the regular CORR. So we want to come down here and we're going to get 16 degrees in whatever minutes that worked out to be. So it looks like we've got 15.56 and 16, or I'm sorry, 15 degrees and 56 minutes. And then we've got 16 degrees and 25 minutes. Are we, yeah, we're going to pass that because we're at 42 point something, right? Okay, so we're going to go past that. So we're going to be somewhere between 16 degrees, 25 minutes and 16 degrees, 55 minutes.
Okay. I can't remember why I had trouble with that. It's simple when you just
yeah, when somebody's explaining it, it's simple, but then you go home and it's not. Okay, so what number do you see as the correction factor if we're in that range?
Hold, let me get my book.
Oh, okay, you don't have your book. Okay, that's fine. Don't get it. So the number works out to be negative 3.2.
Okay.
Okay, so that then is the correction factor. So we do negative 3.2, and we don't need to worry about parallax because it was, I think it said it was a star, right? Let me reread the problem. Yeah, it's a star. Okay, so we don't need to worry about parallax. We don't need to worry about moon. We don't need to worry about temperature pressure. So that's it. So all we have to do is take whatever number we got there, subtract 3 point, did I say 2? I can't read my own handwriting there. Whatever that is. And then that will be the fully corrected altitude.
Then I had trouble with 19. I don't know why.
19.
It's the running fix one on page 15.
Yeah, that's the one where you put in the numbers.
Yeah.
You put it into the smartphone.
Yeah.
Well, tell you what, I want to make sure we get to all the new material.
Okay.
So let's jump in the new material, and then at the end of the class, if we have time, we can spend a little. We can go back and work on that.
I had an error with that one as well, but I figured it out. So it might be the
what
same
was your
thing.
error? Because maybe he made the same error.
So I only, the first time when there was an error, I put in on the iPhone app that I found for course, there's a spot for degrees and a spot for knots or nautical miles per hour or whatever it is. And I didn't put in any for the first measurement, and I did put it in to 40 degrees at 6.44 nautical miles on the second one. And then I redid it with that on both, realizing that I was moving at that speed at both points, and then it gave me the right answer.
Oh, okay.
Okay. All right.
I did that.
So it might have been that.
Yeah. Another mistake that a lot of people make, but I was in the instructions, I was very specifically to warn you about this. Even though both of the measurements were made on May 12th local time, I purposely set this up so that according to in Greenwich, the date changes. So we take our first measurement when it's slightly before midnight Greenwich. And then the second measurement is when it's slightly after midnight Greenwich time. And so if you don't take that into account, that could throw you off. But I did specifically warn you about that in the problem statement.
Yeah.
So hopefully you didn't make that. Okay, well, let's go ahead and jump into the new material. Okay, so if you've done any reading about celestial navigation and worked through any problems, you will have come across this term here, GHA, which means Greenwich Hour Angle. And so what is it? What is Greenwich Hour Angle? Well, it's basically the same as longitude. And in fact, if you are in the Western Hemisphere, let me turn on annotation here. Okay. So if you are here in the Western Hemisphere, your GHA is your longitude. They are exactly the same. But where it gets different is once you get to the international date line, so if you keep on sailing west, So you've now entered the Eastern Hemisphere. And the way that longitude works is, so if you're at the international date line, you're at 180 degrees. And then as you move further west, the numbers start going down. But it's more convenient for celestial navigators if we don't do it that way. For celestial navigators, it's more convenient if we just keep on counting up. So here we're at 180. Here we go to 200, 220, 240, 260, and so forth. So as we approach Greenwich, we zero in. We come up on 100 on 360. It just makes the math easier if you use Greenwich hour angle rather than longitude. Okay, so hopefully that's pretty straightforward. Okay, so the other. Okay, yeah. So if you need to convert back and forth, a good way to think of it is if you're in the Eastern the hemisphere, then GHA is just going to be 360 minus what your longitude is. Okay, okay, so now it's important that we know the geographic position of the object that we measure. So let's say we measure some star, Sirius or whatever. Okay, so we need to know where is the geographic position of Sirius at the time that we measured it. That's in a few minutes, you're going to find out exactly why we need to know it. So the smartphone has all that data built into it. But since we're no longer using the smartphone, we're going to use the Nautical Almanac. And so when you look on page 246, which is a sample page from the Nautical Almanac, you can see, so the numbers here don't match what you have because these are different pages from a different year, Nautical Almanac, but it works the same way. So it tells you what is the GHA of the sun at any whole hour. And let's see, let's go. So 246 actually isn't the page that we want. Let's go to, if you start at 246 and then flip the page twice, you'll come to page 250, except if you look at the bottom, it doesn't say 250 on it. But you'll get a page that looks like this. So up at the top, it says 2005, May 10, 11, 12, right? So that's on page 250 of your book. And so you can see that there is a column here that'll tell you what the GHA of various objects are on these 3 days. So this page is only good for 3 days. So May 10th, May 11th, and May 12th. And then if you had a Nautical Almanac, you'd flip the page and there, each page consists of 3 days, right? And so if I want to know what is the position of the sun at exactly, let's say 5 a.m. Greenwich Mean Time on Tuesday, January the 1st. Okay, so I just look right on here. So at 5 a.m., the GHA of the sun was 254 degrees and 12.3 minutes. Okay, so that means it had already reached the international dateline and kept on going. Okay, and so as long as we make our measurements exactly on the hour, then it's really simple. We don't need to do any interpolation. But of course, that's not going to happen. As you're not going to measure it exactly at 5 a.m. You're going to measure it at 5:23, and so we're going to have, and so on next week's class, we're going to learn how to interpolate between the lines. But for today's class, we're going to assume that we've got nice numbers, so we measure it exactly on the hour. We don't have to interpolate. Okay, so if the sun is what you measured, this is where you look to see what its GHA was at various times. If the moon was what you measured, then this is where you look to find out what its GHA was at various times. And then if you flip over or if you look over the next page without flipping, you'll see that. Okay, wait a minute. Oh, sorry, I'm on the wrong page. Sorry, get back here.
Wait, what did you say, or what is the arrow pointing to? Up next to the names of the planets?
Okay, yeah, so if you look on, let's see, we were on page,
250.
yeah, so we're still on 250. So, okay, so yeah, the sun and the moon, they're on page 251. The planets are on page 250. Okay, so sorry, I got that a little backwards there. Okay, so the arrows up here, those are showing you, oops, sorry, those are showing you basically the same thing for the planets. Let me turn on annotation so you can see. So let's say that you're interested in Venus. So right here, these are the numbers that will tell you what is the GHA of Venus. These are the numbers that will tell you what was the GHA of Mars, and here's Jupiter, and here's Saturn. So those are the various planets, right? So if you measured any of these objects, this is where you would look to see what was the GHA of the planet at that instant that you measured it. Now the stars are a little different. Let's go take a look at how the stars work.
So is this basically the GP of those things by longitude?
Yes.
Okay.
This is how you know the longitude GP. And then in a minute, we're going to talk about the latitude portion of the GP, but this is how you find the longitude part. So speaking of the latitude part, let's go ahead and talk about that now, because that's my next slide. Okay, so another word that you need to know that you may have heard before is declination. Declination basically tells you what is the latitude of the GP of the object that you measured. Okay, so we just call it declination, but declination and latitude, you can just use the two interchangeably, and you don't need to worry about, you know how longitude, it's a little bit different because if you pass the international date line, then it's a little different. Well, with declination and latitude, it doesn't matter. It's exactly the same. Whether you're north of the equator, south of the equator, it's exactly the same. Okay, so then this is where you would look to find out what is the declination of the various objects. Now, if you look at the declination of the sun, you'll see it's changing. I mean, not terribly fast. I mean, it's 20 on this particular page here, it's 23 degrees, basically all day long. Now, if you look in your book, you're going to see it's different numbers because your book here has May, whereas my book has January. So that was the difference. So if you look here in your book, you'll see that on May the 10th at exactly midnight, the declination of the sun was 17 degrees, 35.3 minutes. And if you look down there, it stays 17 degrees for quite a long time. And then on Wednesday at about 1400 hours, then the declination went up to 18, and then it stayed there. So you can see the declination of the sun is changing at a rate which we need to take care of. But I mean, it still is within 1 degree over a whole 3-day period. Okay. The moon works the same way. So over right here is where you look to find out what the declination of the moon is. And you can see that it also changes appreciably over the period of 3 days, but not horribly, you know, maybe plus or minus a degree or two, but not horribly. And then for the planets, it works the same way. Let me go back up here. Okay, so again, for the planets, the declination for them is, so here's the declination for Mars, here's Jupiter, here's Saturn. Okay, so you just look those up. So those are nice and straightforward. And so by looking here, you can find out what is the GP of the object at the time that you measured it. And that's that, nothing more to it. Stars are a little bit more difficult simply because there's 57 navigational stars, right? So if we were to do the same thing for the stars that we've done for each of the planets here, the nautical almanac would have way too many pages in it. So there's that easy workaround for that. So this is the workaround. Okay. So what we're going to do is we're going to introduce a new concept called GHA of Aries. and another concept called SHA, which is sidereal hour angle. So let's find out what those mean. Okay. So here is my favorite star chart. And there is a symbol on the chart right here that looks, it's basically, this kind of a symbol. Okay. That is the symbol that's used to represent Aries the ram. If you're into astrology very much, you know that each of the different astrological signs has a little symbol that they use. So this is the astrological sign for Aries. And so if we draw a vertical line through that symbol there, this vertical line is basically the celestial prime meridian. This is the equivalent of 0 degrees longitude for the sky. All right. And so what we're going to do is when we're measuring how far east or west a star is, we'll just measure how far it is relative to our origin here. So let's say that I've got the star Aldebaran. Okay. So however many degrees it is from our reference point to Aldebaran, that is what we're going to call the SHA, which S stands for sidereal, which is, I guess it's Latin. It means star. Okay. So the sidereal hour angle of a star is measured relative to the celestial prime meridian, and that's something that never changes. So what we can do then is if we want to keep our nautical almanac as short as possible, rather than publishing the GHA for every single one of these 57 stars, what we can do is we can just publish what is the GHA of our origin, which is called GHA Aries, and then we just add whatever the sidereal angle is for whichever star it is that we're interested in. So let's see how that works. Let's do an example. All right, so here's our celestial prime meridian. Okay. Oh, and by the way, if you use this other chart, then the left and right edges of the chart, that is where the first point of Aries is. Okay. So if you are a celestial navigator, we talk about SHA. If any of you are into astronomy at all, astronomers, they do it the other way around. Rather than starting from the left side and counting to the right, they start from the left side, which is the same thing. I mean, the first point of Aries here and the first point of Aries here, it's the same thing. But what they do is they count to the left rather than to the right. But let's not worry about the way they do it. So this is what we're going to do is we're going to measure it this way. Okay. So let's suppose that we've measured some star and we need to know what is the geographic position of the star at the time that we measured it. And so we look in the nautical almanac and they don't have a GHA for the star, but they do have a GHA for Aries. And so let's suppose that we look in here and it tells us that at the time that we measured the star, the GHA of Aries was exactly 60 degrees. Because remember, I told you I'm going to keep the numbers simple. Now, in reality, it's going to be like 60 degrees and 24.3 minutes. So in reality, we're going to have to do some interpolation. But for tonight, we're going to keep it simple. Nice whole numbers. So we're going to look in here and we say, okay, the GHA varies at the time that we measured this particular star was 60 degrees. And then we look in the table over here, and it tells us what is the SHA for all 57 stars. And so we look for the star that we measured. And so let's suppose that it tells us that the SHA of the star that we're interested in is 55 degrees. So then that means that the GHA of the star that we are interested in is 60 degrees for Aries, plus another 55 degrees for the star. So that means the GHA of the star then was 105 degrees at the time that we measured it. Pretty straightforward. Yeah. And so as long as the geographic position of the star is in the Western Hemisphere, then the GHA and the longitude will be exactly the same. And then once the GP of the star gets over in the eastern hemisphere, then you know the longitude and the GHA won't be the same number anymore. But it'll make the math a lot easier if we think in terms of GHA rather than longitude. So that's how it works for stars. Any questions? Okay. All right. So it's really nice
just-
because, go ahead.
They're just added together, GHA and SHA.
Yep.
And
Just
that's the
add them
total.
together. That's all
Okay.
you do. So if it weren't for this the technique of using the GHA together with the SHA, our nautical almanac would have to be thousands of pages long, and that's just not doable. So this is where you look to get the GHA of Aries, and then this is where you look to find out what is the SHA for your particular star. And while we're at it, you'll notice that they also have the declination there, and they only give one number for the declination. And that's okay because the declination of a star does not change enough over a 3-day period to worry about. Now, if you were to get out your nautical almanac, if you look up what the declination of some star is in January, and then you flip back and you find out what is the declination of that same star in October, you'll find out that the declination of the star will have changed. Not very much, but a little bit, okay, over the course of a year. But over the course of 3 days, it doesn't change enough to worry about. So they just give you one number and that's it. So we just use that. So there's the declinations or the information for the stars there. Okay, so I think that's good enough there. All right, so now we know how to find the GP of whatever star it is that we measured, assuming that we measured it right on the hour, and assuming that the numbers are nice integer degrees. So now that we know what the GP is, now it's time to plot what our position is. So the traditional way of doing this is using books. And there are two sets of books here. Okay. This book here is called HO 229. And this book is just nothing but a bunch of tables, a bunch of numbers. And so what you do is you flip through this book, and depending on what your estimated position is, and depending on various other things, that tells you which page to look on. And then you look up a number here, and then you go back here and look up another number, and you just add some things together. And then you can figure out what your latitude and longitude are from that. And so this is the traditional way of doing it. I am not planning to talk about that today, and maybe not even next week either, because there's another way that I think is a lot easier. But also there's another problem. You probably can't see it very well, but this book here tells you that it's only valid if your estimated position is somewhere between 30 and 45 degrees. If you are somewhere else, you need to get volume 2 of the book, of the series. This is volume 3. So there, for every 15 degrees of latitude, you have to get a different book. So if you want to sail anywhere in the world, anywhere from the equator to the pole, you need to buy all 6 volumes of this book, which is a big pain. And so if you've done much study online, you may have noticed that most celestial navigators, or I'm sorry, most recreational sailors do not use this book. It's just too much trouble. So most of the people that teach celestial navigation for recreational sailors tell you to use this book instead. This book is called HO 249, and this is basically the same book as HO 229. Just a bunch of numbers there, except there's only one volume of this. Okay, But again, so this one covers a slightly wider latitude. This is good anywhere from 0 up to 40 degrees. But if you go above 40 degrees, this doesn't work. And also the stars that you measure, you can't measure just any old star. The star that you measure has to be a star where its declination is somewhere between 0 and 20 and 29 degrees. So this book is a little bit easier to use than the other book, but it also has some serious drawbacks. And I think that there's an easier way completely. And by the way, so does the author of your book here. The author of your textbook agrees with me that it's actually easier if we just use a simple calculator. And so what we're going to do tonight is we're going to use a simple calculator, and you'll see, at least I hope you'll see, that this one $10 calculator can replace all 6 volumes of the HO 229 book. And so it can cover the entire range, no matter whether you're at the equator or at the North Pole or anywhere in between. All you need is this one calculator, and all you need is one equation. It's a little bit of a complicated equation, but this one equation and this one calculator, that's actually what these books are, is all of the numbers that you see in these books. These are just the solution to this one equation for all sorts of different possible input out values, depending on where you are. Okay, so that's going to be our strategy for tonight. And maybe we'll also stick with this next week as well. We're just going to take this one calculator and it's going to do everything for us. And it doesn't even have to be a programmable calculator, but it does need to have trigonometry capability. So you see the buttons here that say sine, cosine, tangent. You need to have those on there. So did you guys get the email that I sent you late last night asking you to get a scientific calculator?
Yep.
And you have it with you? Okay, good. All right, so that will make it very easy to do what we need to do tonight. Okay, now, so if you got the email, that means you also got the link that I sent you to this spreadsheet. So this is a Google spreadsheet that I created that this does all the work for you. I mean, this is almost as lazy as using the smartphone. But it's really nice because it helps to check your work, make sure you did everything right. So we'll talk about that later. So drum roll, let the math begin. Okay, so the next hour or so is probably going to feel like a math class. And so you're going to feel like you're back in high school in your trigonometry class. Or maybe you didn't even take trigonometry. If that's the case, this might seem overwhelming. So if what we're going to do over the course of the next hour does feel overwhelming, well, just remember the smartphone will do all this for you. So you don't need to do this if you don't want to. And also that Google spreadsheet that I sent you, that also does all this for you. So if you don't want to get into the gruesome math, you don't have to. But if you are interested, here it is. We're going to dive into it. Okay, so I'm going to start just by reminding you of something that we've already talked about, but it's worth reminding you because it's crucially important that you understand how this works. Okay, so the idea is that when we measured a star, so let me turn on, every time I change slides here, I have to turn the annotation off and then I turn it back on again. Okay, so let's say that we measured this star. And so what we're going to do is we're going to find out what was the GP of that star at the time that we measured it. And then we're going to take our sextant altitude and we're going to take 90 minus it, because remember, what we really care about is not the sextant altitude. What we really care about is what we call the zenith angle, which is just 90 minus the sextant. Okay, so the zenith angle, that will tell us how far we are from the GP of the star at the time that we measured it. So then we know that we're somewhere on this circle here. And then what we do is we measure a second star, and we look up in the nautical almanac to find out what was the GP of that second star at the time that we measured it. We look at the sextant altitude, correct for all the things we have to correct for, and then do 90 minus it. And so then that tells us that we're somewhere on this circle, and where those two circles overlap, that's where we are. So, so what we could in theory do is, in theory, we could get a big globe, which I should have thought to bring a globe, but pretend that I've got a globe here, okay? And take a pencil, and we could just draw some circles on the globe, and then we'll see where do the circles overlap. Okay, yeah, I mean, we could do that. The trouble is that the magnification of the globe is such that even if we use a super sharp pencil, still the width of that pencil line is, it could be 100 miles, right? And we need to know our position better than that. So drawing circles on a globe is not going to do the job for us. In theory, yes, but in practice, no. Okay, so what we're going to do instead is we're going to set up what's called the nautical triangle. And so the procedure is this. You see step one. Let me turn on, okay. So step one here is you make a guess for what your position is. And so that's going to be your dead reckoning position that we talked about before. Okay, so we put a point right here, and we say this is where we think we are. We recognize that it might be wrong. In fact, we recognize that it will be wrong, but it's close, right? And so it's a starting point. And so then what we're going to do is we're going to draw the navigational triangle, at least in our mind. And so the navigational triangle is the triangle where at each of the 3 points of the triangle are 3 important things. At this vertex down here is our estimated position. This vertex over here is the GP of whatever object we measured. And then the third vertex of the triangle is the North Pole, and it will always be the North Pole. And so what we have here is a triangle. Now, you might say, well, how can a triangle have curved lines? Well, we're not drawing this triangle on a flat piece of paper. We're drawing this triangle on the globe. And so, yeah, so this side, let me switch to a fatter pen here. So this side right here, it is the side of a triangle. It makes sense to call it a side of a triangle, even though it's a curved line. And when we measure the length of that side, rather than measuring it in nautical miles or meters or normal units of length, we're going to measure it in degrees. We're going to say, how many degrees long is this arc? And so that takes a little getting used to, because normally when we talk about degrees, we're saying like this angle right here, how many degrees is that angle? That makes sense, right? But we're also going to use degrees to measure the length of the arc there. And that makes sense, because if you were to, let's say we put a dot right here at the center of the Earth, and we have an arc here. So this angle right here, well, yeah, it makes sense that we can use angles to measure degrees. Okay. All right. So what we're going to do then, once we've got our nautical triangle, is we're going to use our mathematical skills. We're going to use trigonometry to calculate what this distance right here would be. That yellow doesn't show up very well. Let me try black. Okay, a little bit better. Okay, so we know what the boat's latitude and longitude are. At least we know the estimated. Okay, so we have a firm number for what the boat's estimated latitude is. We have a firm number for what the star's latitude is. Okay, and we have a firm number here for what is the difference between our GHA, or if you prefer, our longitude, and the star's GHA. And so what that means is we know this angle right here that I'm hope you can see. Okay, so that means we then know how long is this side of the triangle. We know how long is this side of the triangle, and we know what this angle is in between those two sides. if you know two sides and the angle in between, you can then calculate everything else that you need to know about this triangle. You can calculate how long this side of the triangle is. You can calculate what this angle is. You can calculate what that angle is. All you need is two sides plus the angle in between, and then you can calculate everything else. Okay, so we're going to do that. We're going to calculate. In fact, let me click here so that I can bring up the next one here. Okay, so we are going to calculate what this distance right here is. Now remember, this is the distance between the GP and the place where we thought we were, but we know it was wrong. But that's okay. We're going to come up with a number for that distance. We're then going to compare that with our sextant reading, because when we take our sextant reading and then do 90 minus it, that will tell us what the real true distance is from where the boat really truly is to the GP. So now we have two numbers. We have what the distance would be if our estimated position was correct. And then using the sextant, we can calculate what the distance really truly is. And we can see whether we are closer to the star than we thought we were or further from the star than we thought we were. And we also know exactly how much closer and exactly how much, or exactly how much farther. Okay. And then from that, we can then draw our position. So, okay. All right. So that's where all this comes from. So I realize I hit you with a lot of stuff really fast. So let me go in and let me give it to you a second time, but this time with pictures to help you understand it. So remember back on the very first day of class when we were learning how to use the smartphone, we had this map right here. And so what we said was that our estimated position was this dot right here, which we knew was wrong, but that's okay. It's a starting point. And so we draw our estimated position on the map. Right? And then we say, okay, let's suppose that we do the math and we find out that the distance, our actual distance from based on our sextant is longer than the calculated distance based on our estimated position. And we find out that the difference is 23.1 miles, and our actual distance from the GP is greater than the calculated distance based on our EP. So what that means is that if we could figure out what direction the star was, and then we point towards that star, and in fact, let's do that. Let's not just talk about it, let's actually do it, okay? So let's suppose that this dotted arrow here is the direction that you would point to if you wanted to go to the star. And so our calculations tell us that the calculations based on the sextant number gives us a distance that's 21.3 miles greater than the distance we get when we solve the nautical triangle. So that means that we're 21.3 miles away from where we thought we were. And so that means we're somewhere on this LOP. And then we're going to do the same thing for the second star. So let's suppose that the second star is located down here. And so again, what we're going to do is we're going to solve the nautical triangle using our trigonometry skills. And we're going to calculate what is the distance from our estimated position to the star. And then we're going to take our sextant reading. And from that, we're going to figure out what is our true distance to the GP. And this time we're going to assume that our true distance works out to be 14.9 miles less than our estimated one. So what that means is that this time, in order to draw our LOP, we are going to have to go toward the star rather than away from the star. And we go 14.9 miles toward the star. And then where those two LOPs interact, that's where we are. Okay, so that's the process we're going to follow. Now, in reality, we shouldn't just go with two LOPs. We should actually do a third LOP, but let's not worry about that. Let's suppose that we're willing to live with two LOPs. There we are. And remember, LOP means line of position. Right? So that's the process that we're going to go through. So give me thumbs either up or down. Does, in theory at least, does that make sense? Kind of a so-so, okay. But it kind of, all right. So what we'll do then is let's actually go through the process and let's see how it works. Okay. Now, I'm cheating here on this slide here. I am using an actual nautical chart. 99% of the time, you are not going to be able to use a real nautical chart because you're not going to be close enough to the coastline to where a nautical chart is going to be any good. So you're going to have to use a special chart called an open ocean chart, which we will talk about in a few minutes. But I put it on this map of San Francisco just to help you visualize what's going on. But in reality, the chart we're gonna work with is an open ocean chart that does not have any features on it. It's just a blank page, and yet we will see that we can still use it quite well. Okay, so first off, let's talk about how trigonometry works. And so don't worry if this sounds like a math lesson. I will keep it. I'll keep it just to the basics. Actually, let me stop for just a second. I know I wrote this down, but I forgot. So, Paul, did you at any point in your life take trigonometry? No. Okay. Alex, did you at any point take trigonometry?
Yes, I really
Okay.
liked it.
All right. So when I talk about sine, cosine, tangent, you know what I mean, but Paul does not. Okay. Well, don't worry about it, Paul. We'll get through this. Okay. So, okay. Even if you didn't take trigonometry, you hopefully learned something called the Pythagorean theorem. And what that means, what that is if you have a special kind of a triangle where one of the angles of the triangle is exactly 90 degrees, we call that a right triangle. And right triangles are really nice. They follow certain rules. And one of those rules is that if you know how long any two sides of this triangle are, you can use this equation right here to calculate what the third one is. And the convention that we always go with is that side C is always the longest side. A and B doesn't matter. I don't care if this one's A or B. I don't care if this one's A or B, but I care very much about this one. C has to be the longest side. Okay. Now, speaking of naming conventions, notice that the letter that I'm using for the sides is always a lowercase letter. And the letter that I use for the angles is always an uppercase letter. And also notice that if this is angle A, the side that's opposite is always side A. So this is angle C, the side opposite is side C. This is angle B, the side opposite is little b. So angles are always capital letters, sides are always lowercase letters, and C is always the longest side. Okay, so if you've got a right triangle, then this equation right here, you can use that to figure out if you know any two, and if you know any two of the sides, you can use the Pythagorean theorem to figure out what the third side is. So even if you never took trigonometry, hopefully you at least studied this one. Okay, and even if you didn't, well, now you know it. Okay, so it works great as long as the triangle is a 90-degree right triangle. What if it's not a right triangle? Well, it turns out that there's another equation which starts off looking exactly like the Pythagorean theorem. Notice it's c squared equals a squared plus b squared. So that's exactly the same as what we had before. But this time we've got this additional term right here, which corrects for the fact that it's not a 90-degree angle. I mean, you look right here, see this angle right here, not 90 degrees. Okay. So by using this one, this is basically the Pythagorean theorem corrected for the fact that this is not 90 degrees. So this is the more general equation. And so again, by using this equation, what we can do is, if we know any two sides of the triangle, and if we know what is the angle in between them, we can then use this one equation to figure out everything else we want to know about this triangle. We can use this equation to figure out how long side C is, because A is a known number. Remember, this is little a now, so this is side A. So little a is a known number, little b is a known number, and here's little a again, here's little b again, so those are known numbers. And this time, notice it's a capital C, not a lowercase c. Okay, so that means we know this, we know this, we know this. So we can use this equation to figure out how long this side is. And then once we know that, okay, now we know all three sides of the triangle. So then we can use this equation again to figure out what these other angles were that we didn't know. Now, I'm not going to go through exactly how to do that. I'm just going to throw it out there that if you know this equation and you're good at algebra, bingo, you can completely solve this, every side, every angle you can figure out for the triangle. Okay. So maybe you saw this in your high school trig class. A lot of high school trig classes don't teach this, but hopefully it did. And so Paul, I realize you didn't take trig, but trust me, this equation works. I'm not going to derive the equation for you. I'm just going to say, here it is. Trust me, it works. Okay. Now this works great for triangles that are drawn on flat pieces of paper, but that's not what we have. We have triangles that are drawn on a globe. And so when the triangle gets drawn on the globe, that complicates things a little bit. So now what we have is we have what's called the spherical version of the law of cosines. So it's a more complicated, more scary looking equation, but it does exactly the same thing that we did before. So if you know how long this side is, and if you know how long this side is, and if you know the angle in between them, you can then calculate how long this guy is. And once you know that, okay, now you know the length of each side. So now you can use this equation to figure out what are the angles. Okay, so this one equation can tell you everything that you need to know about the triangle. But in order to use this equation, you need to know how long two of the sides are. It doesn't matter which two, but in any two of the sides, you need to know how long those are, and you need to know what is the angle in between those two sides. So as long as you have that information, then life is good. You can then figure out everything else about this triangle. You can figure out how long this side is. You can figure out what this angle is. You can figure out what this angle is. So you know everything that you need to know about the triangle just using this one equation. Now, if you've never had trig, this is a scary looking equation. You say, what is this COS? I've never had, what is that? What is this SIN? What is that? Well, if you've never had trig, then that's going to be a little bit to explain. So what I did was I anticipated there would be people in the class who had not had trig, and so let's see. Let me figure out a little bit out of order here. Where did I put this? Let me look in my thing here. Okay, yeah, here it is. Let me go back and share this with you again. Okay, so if you look on page 41 of your workbook, you'll see a little primer that I have created that teaches what is a sine and what is a cosine and all that. So we don't have time today for me to explain what is a sine and what is a cosine. But if you go to page 41 of the workbook, and you start there and go through page 42, 43, 44. I forget how many pages, but there's like about 5 or 6 pages that's basically just a mathematics textbook that will tell you what is a sine and what is a cosine. So all I can recommend that for right now is just later, after class lets out, go through and read this thing, and hopefully it'll help make things clear. But a sine is just something that you can do on your calculator that in fact, we're going to do in just a few minutes. Okay. So I'm going to have to ask you to just kind of take it by faith for right now. Okay. Okay, so let's go back down here again. We've already gone through this. Okay, so let's see how we would do this in real life. Okay. So what we're going to do is we're going to assume that our estimated position is what you see on the screen right here. Let me turn on annotation again. Every time I change slides, I have to turn annotation off, and then I have to turn it back on again. It's really annoying. Okay, so right here, this is our estimated position. Our position, which we know is wrong, but that's okay. All right, so we're going to assume that our latitude is 16 degrees. Our longitude is 138 degrees west. Okay, and so then we measured a star, and then we looked in the Nautical Almanac to find out what was the geographic position of the star at the instant that we measured it. So let's suppose that the Nautical Almanac tells us that the declination, which is another word for the latitude. So the latitude of the GP at the time that we measured it was 37 degrees. So that means this here is 37 degrees. And for our boat here, we said it was 16 degrees. Okay, right? And the GHA of the star at the instant that we measured it was 206 degrees. So that means if we start at the Earth's prime meridian, if we go westward 206 degrees, then that will be where the star is. And for us, our longitude was 138 degrees. So again, start at the prime meridian and go westward 138 degrees. So if our longitude was 138, I prefer to call it our GHA. If our GHA was 138 and the star's GHA was 206, then when we draw the nautical triangle here, this angle right here will be whatever let me try that again. So whatever 206 minus 138, whatever that number is, that will be the angle right here. Okay, that makes sense? Okay, so let's draw this here. Okay, so our latitude was 16 degrees, so that means we're 16 degrees above the horizon. The star's latitude or declination, I'm going to use the words latitude and declination interchangeably. Purists get mad at me for doing that. Purists say, well, if it's a star, you should call it declination. Yeah, same thing, right? So we're at 16 degrees above the equator. The star's GP is at 37 degrees above the equator. Okay, so we can then draw the triangle. So if we're at 16 degrees above the equator, and we know that from the equator to the North Pole is 90 degrees, then this side of the triangle must be whatever 90 minus 16 is, which turns out to be 68. Okay, so 68 degrees, that is 90 minus 16. That's how I got that. So we know that the distance from the North Pole to our estimated position is 68 degrees. Do the same thing with the star's GP. So the latitude of the star's GP is 37. So if we take 90 minus 37, that tells us what is the distance from the star to the North Pole. So that works out to be 53 degrees. Okay, and so, oops, wait a minute. Sorry, I just made a mistake. 90 minus 16 is not 68. Sorry, the 68 degrees, that's something else. So the 90 minus 16 is 74. So the distance from the boat to the North Pole, that's 74. The 68, where did that come from? That's if you take 206 minus 138. So 206, so the star's longitude effectively, the star's GHA, minus our GHA, okay? So that is equal to 68 degrees. So that tells us that is what the angle is in between these two sides. So we now have enough information that we can now solve the nautical triangle. We now know how long this side is. We know how long this side is. We know how long the angle is in between them. And so now all we have to do is use that equation that I gave you, and we can then solve for this length. And that will then tell us how far, that will tell us what is the distance between the star's GP and our boat's estimated position, which we know is wrong, but that's okay. So once we know what this distance is, then what we can do is we can get out our sextant and take our sextant reading and take 90 minus our sextant reading. That will tell us what the real true distance is from the GP to where we really truly are. And then we just say, okay, then we know how far away is the LOP from our estimated position, and we can draw an LOP there. That's the process we're going to go through. That makes sense? At least in theory. And don't worry, we will do an example, okay? But at least in theory, I would hope that that makes sense. So let's do,
all of this depends on your initial estimated position.
right. And it's
Well,
okay. It's okay that your estimated position is wrong.
that's the part I don't get. It kind of seems like garbage in, garbage out. If you know your position, you know your position. If you don't know your position, you don't know your position. And how do you get your position from estimated numbers? I mean, how does that work?
Okay, let me go back to my sharing screen. Okay, so where you see the boat is, okay, this is a point that you could draw a point on the globe. Even though you know it's not really your actual position, that's okay. It's a point on the globe. And so if you take this point on the globe, you can draw the nautical triangle here. Okay. And you can calculate what is the distance from the star's GP to this point that you drew on the globe. You can calculate that distance with great precision. So do you agree that that is something that you can calculate to a high level of precision?
Well, yeah, but I could also put a point in the globe down on the southern hemisphere and calculate that to a high level of precision too.
Okay, good. All right. So if you
And
agree
my
that
boat might be on, my boat might be on the equator.
okay, all right. So if you agree that you can put this point anywhere you want, and then you can calculate to a high degree of precision what is the distance from the star's GP to this fictitious point, you can calculate it to a high degree of precision. So now here comes the important part. What we're gonna do now is we're gonna take our sextant reading, and remember that the sextant reading is the altitude, which is not really what we want. What we really want is the zenith. Okay, so we take the sextant reading and do 90 minus it, and we get the zenith. Okay, so that number, the zenith angle, that tells us what is the real true distance from the star to where we really truly are. So that allows us to draw a circle here. Okay, so we know that we are somewhere on this circle. Okay, and notice that this circle did not go through where the boat was. The circle is farther away from the star than the boat was. But we know this real true distance. So we've got two distances. We've got the fictitious distance, and then we've got the real true distance. So do you agree that those are two numbers that we can calculate? Okay, so now here comes the magic. What we do is we look at the fictitious distance compared to the real true distance. And so if the real true distance, let's say that it's 12 miles bigger than the fictitious distance, then what we can do is we can point our arm in the direction toward the star, and then we can turn around and go in the opposite direction by 12 miles. Because our real true distance is 12 miles bigger than the fictitious distance. So if we take the fictitious point and go in the opposite direction away from the star by a distance of exactly 12 miles, then bingo, we're on the LOP.
Okay.
You don't sound 100% convinced.
I'll chew on it.
Okay, all right. And remember, this is all being recorded. So you can go back and watch it a second time later. And also remember that everything that I am talking about here is described in this book. And this is a great book. I think the author here did a great job. So I have my way of explaining. What's that?
Yeah, go ahead. I got to catch up on reading that.
Okay. Well, I don't expect that you've read it yet, but I do expect that after you've listened to my explanation, go through and read his explanation. He explains things using slightly different wording than I do. And so, when you see it from two different perspectives, that usually makes sense. Okay. So here's how we got the numbers from. So this distance right here, what I'm going to call the fictitious distance. Okay, that's what we're going to calculate using our trigonometry skills. And so then we're going to compare that to our real true distance. And so we're going to use this scary looking equation, and it will tell us the fictitious distance. So we're going to put the numbers into the scary equation, and the number that comes out will be the fictitious distance. And so I'll show you in a minute how this works. And then we compare that to our real true distance, and then that gives us our position. So let's do a little bit of math here. So let's go back here. Okay, let's take these numbers that I put in here, and let's get out our calculators, and let's see if we can calculate what is the fictitious distance. Okay, so I'm going to use the numbers that you see on your screen here. I'm going to assume that our estimated position is 16 degrees north, 138 west. The star's geographic position is 37 degrees north and 206 degrees west. Okay, and so let's get the nautical triangle out, and let's do some calculations. All right, so I've got a bunch of mathematics here where I've done some algebra to rearrange the equation, and I'm not going to take the time to go into it. But at the bottom there, that's the equation that we want. Okay, so here it is. So this is what we want to put into our calculator. We just got to figure out what numbers are what. All right, so let's look at the naming convention here. So what I've got is I've got ABC. So B is always going to be the point of the triangle where the boat is. So B stands for boat, right? That's why I chose the naming convention that I did. So vertex V, so vertex is the pointy part of the triangle. So vertex B is the vertex where the boat is located. Vertex C is where the celestial object is located. And I did that on purpose because celestial object starts with C. And so the other one that's left is A, so that one is the North Pole. So our triangle then is going to be, so here's angle A right here. This is angle B right here, and this is angle C right here. And remember, the convention that we use is the angles are always uppercase letters, and then the side that corresponds to the angle. So if this vertex, and let me clear this out. If this vertex here is B, side B is always going to be the side that's the farthest away from that. And so the sides always has lowercase angles. So side B is going to be 53 degrees long, which I realize it sounds a little bit weird to talk about the length of something in degrees, but if you're drawing it on the globe, it does make sense. So if the star's latitude was 37, then that means that this part of our triangle is 53. If the boat's latitude was 16, then do 90 minus it. So that tells us that this length of the triangle was 74. And then the angle in between them is the star's GP minus our GP, which works out to be 68. So we now have the numbers that we need to put into the triangle here. So little b, that's 53. So we're going to put 53 in there and there. Little c, that's 74. So we're going to put that in there, and we're going to put that in there. Big A, that is angle A. So that means we're going to put 68 degrees in there. Okay, so what we want to do then is we want to type this into our calculator. We want to type in, oops, let's see. Let me go back up here again. Okay, all right. Yeah, so, all right, so we want to type into our calculator. Oh, I keep forgetting whenever I change slides, I turn off annotation and then I have to turn it back on again. If I don't turn it on, then I touch my screen, then it does that. Okay, so this is what we want to type into our calculator. We want to type in, so Paul, what kind of calculator do you have?
I have a TI-30, and then
Good.
also the iPhone's calculator. If you turn it sideways, it becomes a scientific calculator.
Yeah, let's use the TI-30.
Yeah,
That's one that I'm familiar with.
calculator.
Alex, what kind of calculator do you have?
I'm using a TI-89.
Okay, all right. So if you're using an 89, you're going to be in good shape. Okay, so let me go to here. Okay, so Paul, what I want you to do is type into your calculator. So notice this. Let me turn on annotation again. Okay. So this thing right here is a cosine with a little -1 above it. So
Yeah.
So if you look on your calculator, you'll see a key that says COS, but then up
Yep.
above the key, you'll see where it says COS -1. You got that? Do you see what I'm asking about?
I don't think mine does that.
I
It's like
promise you it does. Can you find the key that says COS?
yeah.
Okay, and if you look directly above the calculator or above that key, do you not see a COS with a -1?
No, it's a square root. This is a very, very old calculator.
Yeah, but if it's
See?
a T, I mean, I've used a TI-30 many times. In fact, I have a TI-30 lying around here somewhere. Oh, I got a better idea. Tell you what, let me just Google TI-30 and okay, yeah, hang on a second. Okay. Okay, I still can't see it clearly. Hang on a sec. What I'm going to do is I'm going to go to my browser here, and okay, so I'm going to go to a blank page here, and I'm going to type in TI-30, hit enter. Okay, and so let's get an image of a TI-30.
Yeah, the one on the right. Sorry.
This one right here?
Yeah.
Okay.
No, the 3 over.
Oh, 3 over, okay. So it wasn't that one, huh? This one? Oh, this one right here?
Oh, one more. Yeah, that one.
This one.
Yeah.
Okay. All right. Okay. Oh my goodness, you're right. It doesn't say COS. Okay.
Neither does my iPhone.
Um, okay. But it does have a key that says INV. Okay.
Uh-huh.
If you look at this, the second row down the first column, it says INV.
Uh-huh.
Okay, so that's going to do what we want. Okay,
Right.
so what I want you to do is I want you to push the INV button and then
Uh-huh.
push cosine.
Uh-huh. It
All
said
right, good.
90.
Okay, good. All right. And then I want you to type a parenthesis. Now, does yours have parentheses on it? I can't remember.
Yeah.
It does? Okay, good. So you got a parenthesis. And now I want you to push the cos button. And if I remember right, it'll automatically put up a left parenthesis for you. Does it do that?
It doesn't show parentheses.
Oh,
It doesn't have like liquid crystal display.
oh my, okay. Oh, it's a really old one. Okay,
Yeah.
so let's go back here to this again. Does it use RPN? Does it use reverse?
No, it doesn't. Those were Hewlett Packards.
Okay. Okay. Uh, wow. Okay, boy, this.
My daughter, I can probably get a better calculator from them from my daughter. I know she has a relatively new scientific one.
Okay. All right. So, okay. So what I'll do then is I'll just go through here using a new calculator because the calculator that I have on the screen here, this one that you see right here, this is a TI-84. Pretty much, well, most people who are in high school right now, they use TI-84s. There are some people that use a different one, but this is probably the most commonly used calculator in schools today. Okay, so
I
what you
think my
see,
daughter has one of those.
okay, good. So what you see right here is what you need to type into the calculator. So what I would recommend is when you get a calculator like this, come back and watch the recording. And then what you see right here, actually, let me take that back. What you see right here.
Something's wrong with the screen I'm looking at. It's still showing the web browser.
Oh, okay, that's weird. Okay, let me stop the sharing and then restart the sharing. Okay, now are you seeing my PowerPoint?
Yeah.
Okay, good. Okay, so when you have a calculator like this, come back and watch this video again, and then type this. Let me make that a little. Type this right here into the calculator, exactly the way that you see it right there. And when you do that, then this right here will be the answer. Okay. And what that answer means is that will be what we've called, up until today, I've never called it the fictional or fictitious distance before, but I like that term. I think I'm going to use that from now on. So this number that you see right here, that will be the fictitious distance between the star's GP and our fictitious position.
In degrees.
In degrees. Yeah, whenever we measure the length of a side on a globe, we measure it in degrees. Right. Okay, so now we know what the fictitious distance is. So what we need to do next is we need to find out what is the real true distance, and we need to go to the sextant to get that. Okay, so let's go to here. So let's suppose that when we measured the altitude of the star, okay, we got, and then after we corrected for parallax and refraction and all those other fun things you have to correct for, let's suppose that the number that we got was this number that you see right here, 27 degrees and 21.8 minutes, which if we convert that into decimal, that's 27.3633. And the way we convert it into decimal is, you remember that there are 60 minutes equals 1 degree. You make that a little thicker there. So 60 minutes equals 1 degree. So if I have 21.8 minutes, okay, if I take 21.8 divided by 60, I will get 0.3633. So 0.3633 is the decimal equivalent of 21.8 minutes. Okay, so if my sextant tells me that this is the altitude, then I convert it into decimal to make it a little bit easier. And then I say to myself, well, but the altitude isn't really what I want. What I really want is the zenith angle, but that's okay because the zenith angle is just 90 minus the sextant. So I'm going to take 90 minus the number that we just got, and I get the answer then is 62.6367 degrees. So this is the real true distance. So now I've got the two numbers. I've got the fictitious distance and I've got the real true distance. Okay. Alex, you're following along on this and you're okay with everything we've done so far? Okay, so let's compare those two numbers. So let's look at our fictitious distance first. Okay, so our fictitious distance was 63.0336. Our real true distance is 62.6367. So what this means is we are closer to the star than we thought we were. And if I subtract the two, this number right here, this is how much closer we are than we thought we were. So that means that the circle, the circle of position is actually a circle that looks like this. So our fictitious estimated position is outside of the real true circle of position. So that means if we want to get to the circle of position, we need to go in a direction toward the star, and we need to go this distance right here. Now, the trick is, how many nautical miles does this correspond to? Because when we want to draw this on the chart, we need nautical miles. We don't want degrees, we want nautical miles. So what we do then is we stroke our chin and we say, if only we knew how many degrees was equal to how many nautical miles. Any of you guys remember what that is?
Is it 60?
Yeah.
60. Okay. Now, to be completely honest, when they first set everything up, they didn't have a totally accurate number for how big the world was. I mean, they were really, really, really close, but it turned out they were a little tiny bit off. So when they first set it up, they set it up on the basis that was 60 degrees was equal to, or I'm sorry, I think I may have said that backwards. Let me try that again. 1 degree is equal to 60 nautical miles. I may have said that backwards there. Okay, so when they first set it up, that was good. And then later they figured out that the Earth is actually just a little different than what they thought it was. So if you want to be really completely rigorously correct, you need to use a slightly different number. It's actually 63 point something, which I have forgotten. Oh boy, it's embarrassing. I should know that. But it's actually 63 point a little bit more. But tell you what, let's not worry about that. For purposes of tonight, let's just say it's 60 degrees exactly. Okay. All right. So then what we need to do is we take the distance here, which we've said was 0.3969. So take that number and multiply. Oh, no, and I haven't done it yet. Here it is, 60.04. That's the correct number. Okay. So when they first set it up, they thought that 1 degree was 60 nautical miles. Then they discovered they were a little bit off. Okay, so what we're going to do, in order to find out how many nautical miles it is to get to the LLP, we're going to take whatever was our distance in degrees, we're going to multiply it by 60.04. And so there we are. So 23.8 nautical miles. Okay. So if we want to get to the LOP, we start at the boat's estimated position. We go toward the star by a distance of 23.8 nautical miles. And bingo, there's our LOP. That make a little bit more sense now? Okay. So if we had a nautical chart for the waters where we were sailing, we could just draw this on the nautical chart. We could plot our position on the nautical chart, and then we figure out where the star is, which, by the way, I haven't yet told you how we know where the star is. So, but if we knew where the star was, okay, we draw our position, we figure out what direction to go to get to the star, and then we draw a line that's 23.8 nautical miles in that direction, and there's our LOP. Okay, but we got two problems that we haven't talked about yet. One is, how do we know what direction to go to get to the star? And the other one is, how can you draw this on a nautical chart if you're in the middle of the ocean and you don't have nautical charts that are high res? I mean, you have a really low res chart that shows the entire ocean, but that's not good enough. That's too low res. We need a much higher resolution chart. How do you do that? Okay, well, that's what we're going to find out right now. Oops, I didn't mean to do that. Let's go back to here. Okay, so first thing is, let's find out, how do we know what direction it is to get to the star? So there's two ways we could do it. One is, at the time that we measured the star, we could just use a compass and find out what direction it was. But you don't need to do that, because if you can solve the nautical triangle, then you can use equations here to tell you what the direction is to the star. So I've got a bunch of scary looking math here, because what I've done is I've taken our original equation and I've just used some algebra to rearrange it to get it into another form that I'm not going to talk about. And again, here's some more algebra. But after I do the algebra, I get this equation right here. And so this is the equation that I want to type into my calculator. So what I do is I get out my calculator, and I'm going to skip over a bunch of stuff here. Okay, so this right here is what we're going to type into the calculator. Okay, so remember, we've got little b, little a, little c. So if you look on the nautical triangle that we had back previously, little b is one side of the triangle, little c is the other side of the triangle, little a is the side of the triangle that we didn't know before. That's our fictitious distance. So this is the number that we just got through calculating. And then we divide by the sine of little a times sine of little c. And then we take the inverse cosine of it all. And so it's kind of messy looking, but if we type this all into the calculator, then 56 is the number that comes out. Okay? That tells us what is the angle to get to the star. So I'm going to skip over a couple things here. So by using our knowledge of trigonometry, we can figure out that this angle hang on a second, this angle right here is 56 degrees. Okay. So remember, this line right here, let me get rid of this line that you see right here. This is the line from the boat to the North Pole. And so that is 360 degrees. Remember how compasses work. North is 0 or 360. East is 90. South is 180. West is 270. So if we point at the North Pole and then rotate to the left by 56 degrees, then that will tell us what angle we need to go to. So whatever 360 minus 56 is, okay, That's a fifth, that's a sixth. So that would be 304. So that tells us that the heading that we would want to take if we wanted to sail directly from where we are to where the boat to where the GP of the star is, we would sail on a heading of 304, and that would take us to the star. Okay, so now we know where the star is. So, and we know that we're closer to the star than we thought we were. So if we get out our chart and we draw a line that's pointed in the direction of 304, and we go 23.8 nautical miles or whatever it was, then we draw the LOP there. So if you're in the middle of the ocean, how do you do that? Well, here we go. This is how we do it. Okay, so did you guys print out this chart on a piece of paper? Okay, please get it out
Yes.
then. Okay, Paul, you have it too? Okay, good. I can see we're running a little slow here. Are you guys okay if we run a little overtime tonight? Okay, good. Okay. So let me get mine out. Well, okay. Actually, I have a slide for it. Let's just use that slide. Okay, so here is the chart. And we can use this chart no matter where we are in the world. Now, the first thing we need to do is we need to set up the chart. We need to draw some latitude lines on the chart. Well, actually, we've got some lines already on here drawn for us. So the horizontal lines, so those are going to be our latitude lines, but we don't have any vertical lines on here. So we're going to have to draw the vertical lines on the chart. Now, so here's how we do it. First thing we're going to do is we're going to take our assumed position and we're going to plot that. We're going to put a dot right in this position here at the X-ray here. And so our assumed position was 16 degrees north. So what that means is we have just defined that this line right here, we're going to call that line 16 degrees north. And our assumed longitude was 138 degrees west. So that means that this line right here, we are now going to define that that line is 138 degrees west. Okay, now we have two horizontal lines on here. So if the middle line is 16, that means this line up here is going to become 17, and this line right here is going to become 15. So go ahead and label those on your chart. So we now have our latitude lines on the chart. Okay. But now we need to draw the vertical lines for our longitude. Now, if we were at the equator, what we could do is we could get out our compass here, which do you guys have your drawing compass with you? Okay, so get your compass out. So if we were at the equator, then we could get our compass out and we could measure what is the distance between from here to here, because that distance is 1 degree of latitude. So then if we were at the equator, we could take this same distance and we could just step it off here and we could put a line right there. And that the distance from here to here would be 1 degree of longitude. But that's only going to be true if we're at the equator. And the odds of us being at the equator are pretty slim. So what do you do if you're not at the equator? So you guys know that the further north or south you go from the equator, the closer together the lines become. All right, so what we're going to do then is we're going to use this nifty little design that you see in the lower right of the screen. We're going to use that to tell us how far apart to draw the vertical lines on our chart. And what we need to do is we need to say, well, what is our latitude? So our latitude is 16 degrees. So if you look at, whoops, I keep forgetting, got to turn on annotation before I touch the screen. So you see these numbers right here. Okay, so it starts off at 0, 10, 20, 30, 40, 50, 60, so forth and so on. So if we're at 16, we want to take our dividers. So this green arrow that you see here is my poor attempt at drawing dividers using my PowerPoint drawing tools. Okay, so we're going to put one point of the divider right here. We're going to put the other point of the divider right here at the height that corresponds to 16 degrees. That tells us where to draw our vertical lines for to get our longitude things. Okay, so once you've got the divider set to the right distance there, then bring it up here. Okay, so here's a slightly enlarged version of that design down at the lower right there. So here I've used this to get my dividers set for the right distance. And now what I'm going to do is I'm going to bring the dividers up. And so the right point there tells me to where to draw my first vertical line. Then I do the same thing on the left side. And then that tells me where to draw my next vertical line. And so I now have my vertical lines so that my chart is all set up now and ready to use. Okay. Have you guys got your charts set up and ready to use? So give me thumbs or give me some indication when you've got your chart. Say it again.
Go through that one more time.
Okay, let me share my screen with you. Okay, so down in the lower right, you see, okay, right here, this is where I'm deciding how far apart do I want to spread my dividers. So, and let me even go back just because I have an enlarged version of it here. So okay, so here's an enlarged version of what you see in the lower right of the page. Okay, so I have numbers along the right here. So these numbers here correspond to the latitude. So if I'm at 16 degrees, 16 degrees would be right about here. Okay, so I'm going to want to put one of the points of my divider right here. I'm going to put the other point of the divider right here at the exact same height. And so this tells me how far apart I need to spread the legs on my divider.
Why am I picking the 50 instead of the 40 or the 30 or something?
What is our estimated longitude or our estimated latitude?
Oh, okay.
Our estimated latitude was 16 degrees.
Yeah.
That's where that comes
Well,
from.
yeah. Yeah, that's where I put the vertical, but why am I spreading it on the longitude scale to the 50 instead of somewhere else? I mean, I see the 16.
Okay. Okay. Thank you for asking. That's important. Well, notice where the 0 is. The 0 is right here.
Oh,
So
yeah.
if we go there 50 and we go here 10, then from here to here is actually 60.
Okay, got it. Makes sense.
Yeah, thank you for asking that. That's an important question.
Okay.
Okay, so now we know how far apart to put our dividers. So what we do next is we bring the dividers up and we mark off over on the right. And that tells us where to put the vertical line that corresponds to 137 degrees west. Because remember, our estimated position is 138, right? So this tells us where to put the vertical line that corresponds to 137 west. Then we do the same thing on the left side. that tells us where to put the vertical line that corresponds to 139 degrees west.
No, I'm gonna be dumb here. How are we picking those two green spots?
I put I start with our estimated position, which is the cross right here. Okay, so this point right here, this is our estimated position.
No.
And so by using the dividers here, this tells us what is the distance that corresponds to 1 degree of longitude at this particular, at this latitude. Notice if we go up a lot higher, so if we were up here at 80 degrees latitude, then the separation between the vertical lines would only be this much, because the
Yeah.
further up north you get, the closer together the lines get, right?
Yeah, but I understand that part for the right hand part, but for the left hand part where you have those two words dividers in a box, and you're picking where to set your compass along that circle, yeah.
Yeah.
How are you picking which number to put that on?
Well, I put the left side of the divider on my estimated position,
Okay.
and then I use the divider to tell me how far to the right to go. Okay, because the divider tells me how far to go before I need to draw my vertical line. Okay, so if I put the left side of the divider on my assumed position.
Okay, never mind. I figured it out. I got it.
Okay.
Yeah, I got it.
All right. Good.
Okay, got it.
Okay. All right. So this line right here corresponds to 137 degrees west. And then I do the same thing on the left side. This vertical line right here corresponds to 139 degrees west. I now have my open ocean chart all set up. So now I can start plotting my LOPs. Okay. All right. So let's do our first LOP. So the first thing we need to know is when we used the calculator and everything, we calculated that the direction to the star would be a heading of 304. So what we need to do is, if we start at our assumed position and we draw a line that goes off in the direction of 304, that would be a line that looks like this. So this shows us what direction we would want to go if we wanted to sail directly toward the GP of the star that we just measured. Okay. Now the next thing we do is we look at the difference between our fictitious distance to the GP compared to our real true distance to the GP. And remember that our fictitious distance was greater than the real true distance. And the difference between them was 20 something. Yeah, 28.3 nautical miles. That was the difference between the fictitious distance to the GP and the real true distance to the GP. Okay, so what we need to do then is we move along this line that we just drew, and we move a distance of 28.3 nautical miles. Now the question is, how do you know how far is 23.8 nautical miles? And the answer to that question is, remember, use the latitude scale. Always use the latitude scale, because 1 degree of latitude will always correspond to 60 nautical miles, no matter where you are on the Earth. For latitude, it only works at the equator, but for longitude, it works anywhere. Okay, so if the distance from this line to this line, that distance is 60 nautical miles, well, you can just read off the chart here. So there's 10, there's 20, there's 30, there's 40, there's 50. Okay, so if we just put the mark a little bit short of 30, then get it as best you can at 28.3 So then our dividers will tell us that this distance from here to here, that corresponds to 28.3 nautical miles. So once we know that, then we can swing the dividers down like this, and bingo, that is 28.3 nautical miles. And so we know that the LOP is the line that's perpendicular to that. So in other words, the line that's at right angles to that. So if we draw that line, congratulations, we have got our LOP. So we know that our real true position is somewhere on this line. So Alex, you've been awful quiet. Is that a good sign? Does this make sense to you? Okay, I see you nodding. Paul, you okay? Does this make sense to you?
I think so.
Okay. All right, so we've drawn our LOP. Now, we've only got one LOP. We need at least two. We prefer three, but we need at least two. So what we would do then is we would just repeat this process. So let's pretend that we have now measured another star. And so the other star, when we go through the process that we just went through, we find that the distance to the second LOP is 22.5 nautical miles. But this time, let's suppose that our real true distance was greater than our fictitious distance. So that means that we need to go away for this one. Okay, so when we go through the math, we plug the numbers into that big messy equation, then the equation tells us that the star is located at a bearing of 18 degrees. Okay, so remember, the bearing to the star is 18 degrees, and the distance to the LOP is 22.5 away. So what we do is the exact same thing we did before. You know, here, so the star is located up here. This dotted line is the line that's at 18 degrees, but the star is away from us, so we need to turn around and go the opposite direction. And we go 22.5 nautical miles. And again, we use the latitude scale to tell us how far is 22.5 nautical miles. And then we draw a line perpendicular to that. Where these two lines cross, that's where we are. Make sense? Okay.
It's
Now
like what we did before.
Sorry?
It's sort of like what we did before.
Yeah, it's exactly what we did before. Yeah, it's exactly the same thing. Now, we really should use 3, because when you remember, what you always want to have at least 3, so that way you can get a triangle, and then you can look to see how big the triangle is. So we know that we are somewhere in that triangle, and we see that it's a nice small triangle, which is reassuring. And we also see that it's a pretty much an equilateral triangle, which means we did a good job of selecting which stars to measure. So we are somewhere in that triangle. Right? So the last thing we need to do now is we need to convert that into a number so that we can write it down in our logbook. So we need to know what is our latitude and what is our longitude. So what we're going to do then is we're going to draw a horizontal line going from the center of that triangle, going horizontally over until it intersects with our latitude scale. And then we just read off there. So if the bottom line here is 15 degrees, so this would be 10 minutes, 20 minutes, 30 minutes, 40 minutes, almost 50, but not quite. So we're a little bit less than 50 minutes. So when I eyeball that, it looks to me like it's 48 minutes. So our latitude then is 15 degrees, 48 minutes. What about longitude? Well, let's draw a vertical line this time, right? And so whatever is the distance from here to here, that's our longitude. But now we don't have numbers on the scale. So how do we measure what is the distance from this vertical line to our dotted red one. Well, here's where we're going to use our dividers again. What we're going to do is we're going to get our dividers out, and we're going to set them so the one edge of the divider is on the 138-degree line. The other divider is on the line that corresponds to our longitude. And so once we've set our divider for that, then we move the divider over here down to the lower right again. And let me do a zoom. So here's a zoomed in thing of it. And so what we want to do is we want to position the divider so that one of the legs of the divider is in this region right here, somewhere between 0 and 10. Okay. We just put it so it's somewhere in here anywhere. And then we look to see which line is the closest line to the leg of the divider that's over on the left side. Okay. And so we want to position the left leg so it's exactly on that line right there. And then, and once we've got that, now we don't open up, now we keep the divider the same. We don't want to open and close the divider. What we do is we slide the divider left and right until the left leg lines up with one of these guys. And then the right leg will be here. Now we have to make sure that we do this at the height. Oops, sorry. We have to do this at the height that corresponds to 16 degrees, because otherwise the distances are all going to be off. But if we do this at the height that corresponds to 16 degrees, so now we're in business. So the left leg of our divider is corresponding to 30 minutes. And then the right leg of our divider, well, so here's 0. This would be 2, 4, 6, 8, 10. So if we come down here, you see the right leg of our divider corresponds to this line right here, which is 6 minutes. So what we've got is we got 30 minutes that way plus 6 minutes that way. So that means our latitude, this is 36 minutes of latitude. So once we know that, then we can come back and we can say, okay, so did I say latitude? Oh, I hate it when I do that. I meant to say longitude. Sorry. I hope you meant I hope you knew what I meant as opposed to what I said. This is longitude we're talking about, not latitude. I realize it's confusing when I do that. Okay. So that means our longitude then is, here's 138 plus 36 more. So our longitude is 138 degrees, 36 minutes. Our latitude is 15 degrees, 48 minutes. We are done. Okay. So ideally, what we would do is, we would spend a lot of time. And, rather than cramming everything into a 2-hour session here, this should ideally be like a 3 or 4 hour session. But all I can say here is that it's all being recorded. So go back, watch the recording, do it again carefully, and hopefully it'll make sense. Okay. So we are now done with all of the material that I had for tonight. So let's go through here, and so a couple things I'm going to skip over here. Okay. This I think is really important, but I don't think we have enough time. So tell you what, I'm going to talk about this next time, but let me just go through it super quickly, because if you read the textbook, you're going to find out that the equation that I gave you looks very, very different from the equation in the textbook, but they are in fact the same. The upper equation that you see right here, this is my equation. The lower equation, this is the equation that you're going to see when you read the textbook. So like I say, they look like totally different equations. They are not. they are actually the same equation. For reasons that I don't want to take time into now, because we're already 15 minutes over. But this equation, for reasons that I will talk about last time, or the reasons that I will talk about next time, the thing that I call cosine of B is exactly the same as the thing that the author calls the sine of dec. The thing that I call cosine of C is the same thing that the author calls the sine of latitude. And we can go through these one by one. Everything that you see on the top is exactly the same thing as the thing on the bottom, okay? Even including this last piece right here. But we don't have time for me to talk about it today. So let me just show this to you now, and next time we meet, I'll talk to you about it in more detail. So my equation and the book's equation may look completely different, but they actually are the same equation. And we'll talk more about it next time we meet. Okay, so here is your homework. I want you to do problems 56 through 67 in the workbook. And the important one is 67. If you could only do one problem, if you only have enough time to do one problem, 67 is the one that you should do. Because problem 67 is where you're going to go through the process that we just went through. You're going to take some numbers and you're going to reduce them down. You're going to get the open ocean chart, and you're going to have to set up the open ocean chart for whatever latitude you happen to be at. So that, remember, that determines how far apart to put the vertical lines. And then you're just going to go through the same process that we just went through. So if you can only do one problem, 67 is the one to do. But if you have time, I'd recommend that you also do the other ones. Okay. So I realize that I just hit you with a fire hose of information. I apologize for that, but I will send you the link to the recording so you can go through and watch it as many times as you want, nice and slow. Okay, any questions before I end the session? You're muted there, Paul. Paul, you're muted.
Alex, when you did 19, did you get something that looked like this on your phone? Two converging lines on the map?
Let's see. What were the celestial objects in that one? In that question?
Sun, lower limb, 2 sunshots. If you don't remember, that's fine. I'll just work it out some more.
Oh, yeah, so 2 lower limb shots of the sun?
Yeah.
Right. So let me put this back to 0, 0 for the first one. No, I didn't have 2 lines like that.
Okay, I'll try to fiddle with that and figure out what those are.
Okay. And I'm always available via email too, and
Right.
phone. I can only take phone calls really on the weekends. Well, I guess late in the evenings, but anyway, we can work one-on-one.
Wait.
Okay, I'm going to go ahead and end the meeting then.
Thanks.
And then next time we meet will be the last time. And then I'm going to try and make arrangements so that we can go together to Utah Lake and do some practice shots. I think I'll set it up for a noon sun shot. And so are you guys available on Saturdays and Sundays, or only Saturdays?
I could probably do either.
Yeah, I could make either work. Saturdays is preferred, but I can do either just fine.
All right, I'll send emails to the other guys and find out what's their preference as well. All right. Okay, I'm going to end the session. I'll see you guys later.
Okay.
Oh,
thank you. This was just what I got for well, he's gone. So
he's gone now. Okay.
he'll watch it on the video. Okay, thank you.
See you later.